Hi everyone, I'm Harrison, an ML engineer here at Neuralink. And I must say, being an ML engineer at Neuralink is a bit like being a kid in a candy store. When you think of the inputs to most ML systems out there, you might think of pixels, of tokens, or of a user's Netflix watch history. The input to our systems is a little different. It is pure, raw brain power. And when we think about the ML systems we can build here at Neuralink, really we're limited by our imagination and our creativity. There's no reason our ML systems can't do anything that the human brain can do, such as controlling a phone, typing, or even gaming. Right here to my left is actual footage of Alex, one of our participants, playing a first-person shooter against RJ, another one of our participants. Now, for those unfamiliar with first-person shooters, this is not a trivial feat. It requires 2 fully independent joysticks, or 4 continuous degrees of control, as well as multiple reliable buttons. Now, contrary to popular belief, the Neuralink does not simply read people's minds. It's simply reading neuronal activations corresponding to motor intent. So one of the fun challenges with this project was figuring out which motions were going to be mapped to the joystick. We started with the typical left thumb and right thumb, but quickly found that the dominant hand overshadowed the non-dominant hand. My personal favorite is we had one of our participants imagine walking for the left joystick and aiming for the right joystick. So in-game, they were simply doing naturalistic motions, like you might do in virtual reality in Ready Player One. And that was really cool to watch. What we ended up on was the thumb for the left joystick and the wrist for the right joystick. And I challenged the audience to try to replicate their motions. I'm really in awe of them being able to pull this off. I want to talk a bit about the progress to our cursor calibration experience. To my left here, you can see RJ completing his first ever cursor calibration with a redesigned open loop flow where we first gather information about his intent and how to map the neural activity, to the first time he controls a cursor, to the final product where he has smooth and fluid control of his computer. And most remarkably, this experience took only 15 minutes from start to finish. 15 minutes from not... 15 minutes from no control to fluid computer use. Contrast that to a year and a half ago with P1, where that was multiple hours to get to the same level of control and several engineers standing around a table pulling their hair out. There was virtually no need for Neuralink engineers to even be at this session. This was basically an out-of-the-box experience for our participant. And even more remarkably, we're continuing to smash day 1 records, with RJ being able to achieve 7 BPS on his very first day with the Neuralink. Now, such an effective and efficient calibration process is only made possible by high-fidelity estimations of a user intention, or labels. And to briefly illustrate just how challenging of a problem that is, this is an animation of myself trying to draw circles on my desktop with a mouse. Now, the task was simple: draw uniform circles at a constant speed repeatedly. And as you can see by that animation, I am horrible at that. Even though my intent was pretty obvious, unambiguous, the execution was really poor. There was a ton of variation in both speed and the shape itself. To visualize this a little differently, each row here is one of those circles unwound in time with synchronized starts. And you can just see how much variation there is in the timing of each circle as well as what I'm doing at any given point in time. Orthogonal to the labeling problem is neural non-stationarity, or the tendency of neural signals to drift over time. And I think that's honestly a beautiful thing, right? If your neural signals didn't drift, you couldn't grow. When you wake up the next day, you're not the same person you were the day before. You've learned, you've grown, you've changed. And so too must your neural data change. This animation here is a simple illustration of the learned representation by the decoder and how it drifts the further away we get from the day it was trained on. This is one of the key challenges we need to solve here at Neuralink to unlock fluid and product level experience for our users.